Oh, I'm sorry. Right there. Is everybody done? That's apparently I can't see. All right, so in the textbook, he gets into AC power in chapter 20. And I'm gonna save AC for later. Just conceptually, the difference in AC and DC power. Batteries run DC, it forces current to go one particular way. So if I have a battery like that, I'm gonna have current flowing out the positive end and into the negative end, or electron current, or electrons flowing in the opposite direction. The electrons only travel in one direction. The drift speed is only in one direction. Unlike AC, and the symbol for AC power supply would be this. It's alternating current. So in essence, you have the high side and the low side of the power supply is constantly flipping back and forth. In the US, 60 times a second. In Europe, I think it's 50 times a second.
Or better.
Or better. So if I have something like this, I have current flowing this way and then it'll oscillate that way, and it's generally represented, the current would be sort of mapped out by a sine or cosine function. Voltage also by a sine or cosine function, and so on. But probably better to get into how you create AC current later on once we've gotten into the magnetic aspect of electromagnetism. Yeah, so in the US, our current runs like that. In Europe, they still use very similar generation, but if that's sort of the zero line there, in Europe it does that. In the US, or anywhere that uses AC power, it goes the other direction.
Why?
The way that the power is most efficiently generated, it's, I stepped into it. You basically want to have a changing a wire basically running through magnetic field lines. Mm-hmm. And when you do that, it generates a current. And then, so if you have a waterfall, you get a loop of wire, magnetic field, if you're lucky, first magnetic field, not particularly strong, but some places stronger than others. Loop of wire, have a waterfall, hit a paddle, which causes the wires to spin around like that. So you basically have current zipping back and forth, depending upon how the wire is oriented. How you connect that to the power grid uses something known as a coupler. Mm-hmm. In Europe, it's a whole coupler. In US, it's two halves, something like that. The way the coupler is situated differentiates.
Is it just because where you are on the planet, or is it just how they do it?
Yeah, well, it depends upon where you are, because that's how they do it. In the US, there was this big debate over, are we going to go AC or DC? Mm-hmm. And at the time, AC power, thanks to Nikola Tesla, was more efficient over long distances. Mm-hmm. And so, because in the US we had much more land per person than in Europe, AC made more sense. Then there was various other things. Westinghouse is a big advocate, and basically made a fortune off of Tesla, who made very little. And Edison was the big DC proponent. And probably one of the, that's a whole different saga. The electrocution of the elephant, using AC power to make it seem more dangerous. Other questions? Not related to AC versus DC. You can bring some of those questions up again when we get to AC more properly. All right, so we talked about Kirchhoff's rule, the voltage rule. that if I have some DC power supply, and this is, let's say, a 3-volt battery. If I say it's a 3-volt battery, that means that if I'm going across like this, I'm going from the negative to the positive, I gain 3 volts. I know that if I end up back where I started, I should be at 0, because the potential difference between any point and itself is 0. So if I go around, if I gain 3 volts there, what happens across my resistor?
You lose 3 volts.
Yeah. So if we use Ohm's law, which we derived the other day, we have the potential difference, or the voltage is equal to the current times the resistance. In other words, the voltage across that resistor is equal to the current times the resistance. The fact that it's negative, or that you're going to lose it, is outside of this formula. So I lose 3 volts across there, so my potential difference is 3 volts. That's going to be equal to my current times, we'll just say this is a 2 ohm resistor. 3 volts equals current times 2 ohms. So my current, I'll do the math part, and you tell me the units. Amps. Now, if you just looked at this right here, you see that is volts per ohm, which is indeed an amp, which is short for ampere. And who was honored? The only one that takes a guess that who this was named after?
Dr. Ampere.
I don't know if he was a doctor or not, but.
Mr.
With the French accent, there's an accent mark there. Yeah, I don't know, my French accent's always been horrible.
That is capital Omega, right?
Yes, it is.
Not a pi.
That is a capital Omega. It is a horseshoe with the luck running out. Now, as we talked about Monday probably, current is also charge, the charge that passes by a particular moment per unit time. So the ampere, not what I'm gonna do there. All right, so the ampere is also defined as a coulomb per second. Actually, technically, a coulomb is defined as an ampere second. Ampere is a base unit, coulomb is a derived unit. They didn't consult me. So a coulomb per second is also the same as a volt per ohm, which means that a unit of time would be a coulomb ohm per volt.
So it took me 15 coulomb ohms per volts to make it to class. Oh my god, it's gonna make my friend's brains hurt, but I'm
Oh, there are more.
Oh yeah.
All right. Questions up to there? All right, so if I have my power supply here, and we'll make it 12 volts. Cruising along, I've got 3 ohms there, and I've got 5 ohms there. So we're now starting to get into slightly more complex circuits. We have a parallel structure of resistors. And I don't know if it can be seen well enough, there's a connector there. We assume that any wire, that wires themselves have no resistance, that any resistance in the wire is bundled up inside whatever level is the resistor. What is the current flowing out of the battery? Well, there's more than one approach to this. We can do a Kirchhoff voltage loop. I know that whatever current comes out of the battery, it's going to split at this point. Wherever there's a junction, current can split. So I'm gonna have some current flowing this way and some current flowing that way.
Here we go. Do we know if it's gonna be like half? Do we just split 12 in 2?
You will split it, but not in half.
Okay.
Well, sorry, 12 is not the current. Whatever the current is, it will split, but, well, I have two paths here. Am I gonna have more current going across the 3 ohm or the 5 ohm resistor?
3 ohm.
Yeah, the path of lesser resistance. I guess if there's two, least resistance. So I know there's some current flowing out of here. And I'm gonna call this I5, and going across here, I3. So the junction rule, Kirchhoff's junction rule, the current coming out of the battery is going to be equal to I5 plus I3. So the Kirchhoff junction rule, junction/current rule, the total current in equals the total current out. That's supposed to be a capital sigma there.
I thought the capital sigma was the 0 with the.
That's the lowercase.
Okay,
Who raised you?
Wolves, man.
Ah, okay. Yeah, they're constantly getting uppercase and lowercase backwards. I also know that if I use the voltage rule, if I start here and go around this loop and I come back and I get back to here, I'm gonna gain 12 volts here, I'm gonna lose 12 volts here, so I know that there's minus 12 volts going across it that way. So if I do the similar process to what I had over there, I know that my voltage across the 3 ohm resistor is 12 volts. That's gonna be equal to the current times 3.
So, I have a question. The resistors, does it cause it to lose current or just take longer to travel through?
Basically, it causes a jam throughout the entire circuit, but yeah, it causes the current to
Less than
slow down.
Just slow down?
Yeah. Because remember, current is charged per time, so there's less charge passing by any point at any particular time. It's not that it just zips along here, it hits the resistor and then slows down. The resistors are gonna cause it to slow everywhere. All right, so I have, so I3 is 4
Amps.
Oh, by the way, occasionally you might hear someone refer to amperage. I refuse to accept that as a real word. The word is current. It's fewer syllables, takes less ink if you're writing it. Actually, if you just use an I, it takes even less ink. Current is the word.
Not amperage.
That should be the last time that word is mentioned in this classroom. If Carolyn does it, I expect all the rest of you to go, oh, Carolyn, come on. And if you're watching this, Carolyn, you've been warned. I'm also going to do a voltage loop around the top bit. So it comes along, cruises up, goes across here, back down. Because for any path I take, it should be 0 by the time I get back to here, my potential gains and losses. So if I gain 12 volts there, what happens across my 5 ohm resistor?
Lose 12 volts.
So my potential drop across here is 12 volts, and that is equal to the current times 5 ohms. So that's I5. So what's the current across the 5 ohm resistor?
12 amps.
Okay. So if I have 2.4 amps going across the top and 4 amps going across the bottom, how much is coming out of the power supply?
I was thinking 6.4 amps.
6.4 amps. There we go. Because that's just the sum. So this is coming out of the power supply. Do a little PS there. So this is 2.4 plus 4, 6.4 amperes. Alternatively, I could have just found an equivalent resistance, so I know that 1/5 plus 1/3 equals 1 over my resistor equivalent. That is 8/15 is equal to 1 over R equivalent. So my equivalent resistance is 15/8. So I basically reduced that to, I have a 12-volt power supply here, DC power supply. I have an equivalent resistance of 15/8. So I have 12 is equal to 15/8 times I. And so I is 12 times 8 over 15. Doing the fancy math here. 3 goes into this 5 times, 3 goes into that 4 times, and I'm left with 32/5, which is 6.4. Now, when I do my voltage loop, personally, I usually start on the negative side of the battery, go across the battery. For whatever reason, childhood scars, I always do, I like the first number in my equation to be positive. So I'm going to rewrite this in the voltage loop. So I start here, I gain 12. Cruising along, I'm doing the bottom path here. Minus 3I3, because I know I'm going to lose potential, is equal to 0. 12 minus 5I5 is equal to 0. Those would be sort of a slightly more formal way of doing it. I'm just following the path around. But it works for any path. If I start here and I go around the path this way, well, I know current's going to be flowing to the right, so I'm going to gain 5 volts, or sorry, I'm going to lose going across that, so minus 5I5. Coming along here, I'm going against the resistor, or going against the current across the resistor. So imagine that if I have water flowing downhill, well, if I go this way, I'm gaining potential. So plus 3I3 equals 0. That's starting here, working around my loop like that. Kirchhoff's voltage loop rule works for any loop, just as long as I end up back where I started. And you could, I don't know why you do it, but you could start here, do a little figure 8, kind of cruise around a few times here, keep working your way back, just so long as you end up back where you started. So I have 3 equations here, 2 unknowns. These equations are not independent of each other. So you would take just 2 of the equations. Actually, we have another equation over here. I have 4 equations. I guess 3 unknowns. Not independent. And this idea of taking a current junction rule and then taking some voltage rules is that first step, or the next step, towards solving a problem such as, I'm just going to present it, but next week we will get to it. there's a resistor here. In test 1B, there will be a question, the last question will be something very similar to this. Batteries might be flipped upside down, but that's the basic structure. There's a master set problem with it. We'll go over how to do these 3 different ways, or 6 different ways, depends on how you wanna look at it. But that's where we're headed. And on that note, I hope you have a great weekend. Don't forget, test on Tuesday. All right, let me stop this.